Here's 2005, number 1. This is an error resistance question, so that means differential equations. So let's see what we have. Ball of mass m is thrown vertically upward with an initial speed of v sub 0. It experiences a force of air resistance given by F equals negative kV, where k is a positive constant. And notice that those are bold. That means that they're talking about vectors, which means that's why they have the negative in there, because the air resistance force will be in the opposite direction as velocity. The positive direction for all vector quantities is upward. Express all algebraic answers in terms of mk, v sub 0, and fundamental constants. Alright, so part A, does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? Well, let's see. As the ball moves upward with its, of course we always have a gravitational force on the ball, right? Call it F sub g or mg. And here, as it moves upward, it's got its greatest speed, and it's moving up, so that means the air resistance will be down, right? So that's the kV. So we start out like that, and then as it goes upward and these forces act on it, the kV is going to decrease that force because the v is getting smaller, right? Until at the top there's no air resistance at all when v equals 0. So what's happening here? Well, this is the greatest acceleration here, so it's getting less, right? So it's decreasing. So we'll say it decreases. A decreases because the net force decreases. Right, when it's going up, when it's going fastest, that's when it has the biggest air resistance force against it and gravity. So that's when the acceleration is the greatest, and will decrease from there. Part B. Write but do not solve a differential equation for the instantaneous speed of v of the ball in terms of time t as the ball moves upward. I've done that lots of times now, unless of course it's the first video you're ever watching about this. But, probably not. So that's net force is equal to mass times acceleration. The force is acting on the ball. Since up now is the positive direction, we have negative mg minus kv equals ma, right? And then negative mg minus k times, kv equals m times dv dt. And there's our differential equation in v. We could solve that for dv dt, but it's not necessary to do that, so I'm just going to leave it like that. Part C. Terminal speed. Well, the terminal speed happens when the net force is equal to 0, and that's the same as saying that the acceleration is equal to 0. And then going back up to here, if the acceleration is 0, that means we have negative mg minus kv is equal to 0. So the v would be equal to mg over k, but they want terminal speed, which of course is always positive, so that means it's the terminal speed is mg over k. Right, it's the absolute value of that. Probably there's a point attached to noticing that you're supposed to drop the negative sign there. You can check that in the rubric. Part D. Does it take longer for the ball to rise to its maximum height or to fall from its maximum height back to the height from which it was thrown? So does it take longer to rise or longer to fall? Let's see. We've got let's see how we want to approach this. If you think about it in terms of energy, then we have here as the ball rises to this max height and then falls back down again there, starts with its initial velocity and reaches this height here. The velocity is 0. And then on the way up, the acceleration is downward, right? And according to our diagrams here, you can see that it's greater than the magnitude of the acceleration is greater than g. Right? So when you throw a ball up normally, you can use kinematics equations and say it's got a constant acceleration of g downward, but here you can see because of the air resistance force that acceleration is always greater than g. At the very top, it's greater than or equal to. At the very, very top, it'll be equal to g. And then what about on the way down? On the way down, now we've got mg to start with when the velocity is 0, and then as it falls further and further and picks up more and more velocity, the kV gets bigger and bigger. So, oops. The kV gets bigger and bigger. So here on this side, the acceleration is down, but it's the acceleration is always less than gravity. So we're covering the same distance. Here, the acceleration starting with this velocity here, so which is going to take less time. It looks like it's going to take less time to go up, so that means it will be longer to fall. Longer to fall. And part E. On the axes below, sketch a graph of velocity versus time. I'll do this on the graph here. Velocity versus time for the upward and downward parts of the ball's flight, where TF is the time at which the ball returns to the height from which it was thrown. So this is where it returns to that same height. So let's see. We throw it with an initial upward velocity, and this the magnitude, because of the air resistance force, instead of being straight down like this, and initially it's going to be steeper than that. Remember, we're starting with a magnitude that's steeper, so you could almost imagine like if the I'm just going to put a dotted line in here like that. That would be if there were no air resistance, right? It would be a straight line like that. The slope would be negative 9.8. But in fact, now on the way down, we know that the magnitude of the acceleration is greater than that, and then it does something like this. Right? And I guess you can kind of see does it take longer for the ball to rise? You can see that it takes longer for it to fall here, right? That's the maximum height right there. And that is it would take this much time to reach the peak. Right, so I think probably the characteristics, you can check in the rubric, I think the characteristics they'd be looking for are that the graph starts positive, that it's decreasing, that it's concave up, and that's probably about it. Right? So that's what it would look like with no air resistance. This is what it looks like with air resistance. All right.